A few weeks ago, after watching lesson 11 of the fastai course, part 2, I posted a video called The Evolution of Matrix Multiplication. And in this video, after watching lesson 12 of the course, I'm posting a part 2 of the video where I'm going to walk through the different matrix multiplication implementations and then compare the results on a subset of 5-digit MNIST images as well as the full 50,000 image dataset. So a couple of notes. I first ran this on Colab, but I was running into an error when I was trying to use Numba cuda. So I instead am doing this on a 3090 machine, and these are the installation commands I ran. And I've put that at the bottom as well in this notebook, which will be posted as a blog post. So initializing the dataset here, the full dataset is 50,000 images, and it's 28 by 28, so that's unrolled into 784 pixels. And for weights, we have 784 by 10, so imagining like this is the final output where we're multiplying all of our pixels by 784 by a 784 by 10 matrix, so we'll get 10 outputs, for example, for 10 digits. Here are the results I got for the 5-digit subset. There's 10 different implementations that I'm going to walk through. The fastest was the PyTorch @ operator with 18.1 microseconds taking for the 5-digit subset. And the slowest was the nested for loops, 3 of them, 3 nested for loops, and that was 600 milliseconds for 5 images. And then for the full data set, I tried the 7 fastest ones that I saw here. The fastest was PyTorch matrix multiplication with cuda at 541 microseconds, and the slowest was Numba dot product at 3.71 seconds. So I'm going to walk through each of these here. First one is the nested for loops in Python, and I made this image in Excalidraw. So first over here we have 5 images, so that's 5 rows, and each one is 28 by 28, so we have 784 columns. So we have this first loop where we go for I in range AR, so the number of rows in A. Then we go for J in range BC. We have 10 columns in our weights, which is the matrix B in this example. And so that's the second loop. And then the third loop happens along both of these edges. So we have 4K in range AC, so the number of columns in AC, which is the number of rows in our weights matrix. So those are the 3 nested for loops that take place. And we multiply and add those up to get a single value here. And then we go through first row, second column is the second value here, first row, third column is the third value here, and so on and so forth until we fill out the entire 5 by 10 output matrix. So I'm going to run that first, and we're going to take a look at our tensor, and this is going to be our default value, or kind of baseline value that we compare everything to. Let me zoom in a bit. So what I'm going to do, which is what's done in the course, is that we wrap everything in a matmul function, and then we're just going to keep on updating the matmul function, and we're going to test everything with T1 to make sure it's equal. So we're making sure that our implementation is correct. So we run this, and here we can see that it's 826. Run it again, 786, 768. So there's 665, so there's some variability. So the numbers that are presented in this notebook are not going to be necessarily the same numbers that are shown up here. All right, so that's our baseline. That's our most naive implementation. We're iterating through the rows in A, iterating through the columns in B, and then iterating through the number of items, 784 in each of those row and column pairs. And for that output matrix, we're accumulating the sum between those corresponding values, and that's how we build up our 5 by 10 matrix. So, okay, that's our baseline. next version is we're going to replace one of these loops. So we're going to replace this inner loop with a dot product. And that dot product we're going to do in Numba. So revisualizing our matrix multiplication, we still have our two outer loops. So we're iterating through the rows of A and the columns of B, except now instead of iterating through 784 items, we're going to pass this first row of A and first column of B, we're going to pass that into a dot function that we're going to define. That's going to run through a Numba loop where it's going to take the dot product between these two vectors. And that final value of that dot product is going to be our first value here in our output matrix. So this is what dot looks like. This is a very similar loop that we saw before. The length of A is 784. And so we're accumulating the dot product, or the sum, between element-wise multiplication of A and B 784 times. And then this digit decorator is what compiles it with Numba. So these two are just examples, but here's our matmul. And we have for I in range AR, for J in range BC, and then instead of our third nested loop, we now have the dot product operator. So the loop is still happening, but it's not happening in pure Python. So that's going to help give us a speed up. This has to use NumPy arrays instead of torch tensors. So we convert that. The first one is just a test to make sure that our output is the same as our baseline, which it is. And then to save some time, we're going to just run this 10 times and see what we get. So the first time we get 1.14 milliseconds. And it looks like, yeah, there's some variability. You know, it just goes down to 800 microseconds. I think when I ran it earlier, let's see, Numba dot product was 542 microseconds, so not getting it as low this time. But the main takeaway here is that just by removing one of our for loops, we go from 600, so 700 milliseconds down to 700 microseconds. So we have about a 1,000 times speed up. All right, so the second version, version 1. So let's collapse these two. Then we're going to look at element-wise operations. So this is basically going to do the same thing, except it's going to do it in one command instead of using a for loop. So I'm going to take the ith row of A and the ith row of A and the jth column of B, and I'm going to get the element-wise product between the two, and then I'm going to call the sum on that, and that's going to be the first value that gets stored here. So it's basically doing dot product, but instead of doing a loop, it's taking advantage of the element-wise operations. So I'm going to run that, make sure it's the same, and run that, and we get about a little higher, some variability, but it's pretty tight. So this was about 0.7 milliseconds. This is about twice that, but we still get a considerable amount of speed up. And this is still just pure Python, PyTorch. We're not using Numba here, but we are using element-wise operations. So that's version 2. We're still going to keep this idea of dot product, and so we're going to do version 3, which is going to use torch dot. So again, we have two loops in Python, and then here, instead of our third loop, we're just going to have a single call to torch dot, which is the same thing as the element-wise operations, which is going to do the same thing as our Numba dot function. So we run that, and we get about the same, a little faster than our element-wise operations. Okay, so that's the end of our dot product exploration. The next couple are going to be looking at broadcasting, and here's a visualization to look at that. So we have one loop here. We're going to go through the rows of our A matrix, so our images. We're going to take one image, and then we're going to broadcast it. So we're going to add a dimension so that it can get broadcasted across the 10 columns of our B matrix. And then we're going to multiply it here. So it's going to take the element-wise multiplication, element-wise product between corresponding values. And then we're going to do dot sum down the rows, so dim equals 0. And that's going to sum down the rows, and it's going to give us our final value that gets stored in our output matrix. So this is broadcasting. The broadcasting is this additional dimension of adding this none unit axis here. And then when we multiply it by our B matrix, it sees that, okay, B has 10, this has 1, so it's going to broadcast this single A vector, which is 784 elements, to match this 784 elements by 10. So it's going to kind of quote unquote copy this 10 times so that we can perform this element-wise multiplication between these two objects. So here we now have a single loop, so we've removed 2 loops from our Python implementation. Here's the additional unit axis, so that when we perform this multiplication, it broadcasts this axis across the 10 columns. And then we want to take the sum down the row so that we get all 10 values here. Then we'll go to the next row, do the next 10 values, go to the next row, do the next 10 values, and all the way down to the 5th row. So we test that, it looks good, and we run that, and now we're getting another speed up. So as you can see here, I can now run this 50 times instead of 10 times because it's a lot faster. And so now we've gone down from 600-700 microseconds. We've got half of that. So we've got 332 microseconds. So we're moving in the right direction. Version 5 is exactly the same, except what we're going to do is that we're going to use NumPy arrays, and I'm going to compile this with Numba. So we run that. We run this line, and now we are down to 70 microseconds. So we get another, 6x, 7x speed up. Everything else is the same. Okay, so now we're going to look at, that was the end of lesson 11. And so now we're going to look at what we looked at in lesson 12. So we're going to look at Einstein summation, which is something that took me a minute to wrap my head around, but I made this visual in Google Slides to kind of help me visualize, and that's what I'll walk through here. So first we're going to look at the notation here. So we have basically we're listing out the different dimensions in terms of what are the input dimensions and what do we want the output dimensions to be. M1 is the images, our 5 images. M2 is our 784 by 10 weights. So for our M1, we have I by K. So I is 5, K is 784. For M2, we have K by J. K is 784, J is 10. So K is 784, so it's a shared dimension, so we use the same letter here in this notation. And when you use the same letter, it's going to, I guess in this case we're not seeing it, later on we'll see it, but when you use the same letter here and then you don't use the same letter in the output, it understands that you want to sum across that dimension. But here we are keeping this K dimension. So we have I, which is 5, K, which is 784, and J, which is 10. So how I like to think about this Einstein summation right here is that it's an intermediate matrix multiplication step before we do the final summation across the 784 dimension to get our final values. So let's look at what we have up here. If we look at this face of our block, we have 5 by 784. So that represents our A matrix, or the dimensions of the A matrix. Then here we have 784 by 10, and that represents the dimensions of our weights matrix. And what we have here is we have the A matrix row that's 784 elements long, and the B matrix column, which is 784 elements long. We're taking the element-wise product of those two vectors, or those two tensors. And right now, we are keeping that element-wise product as separate. So we're not summing across this K dimension, which we will to do the final step of matrix multiplication. So if you look at these lines here, that kind of represents, we have 784 slices, each which represents the element-wise product between one row in A and one column in B. And so we kind of get this, these slices of intermediate element-wise product. If we were to sum down each of these columns, each of these 10 columns in our J dimension, we would get our final matrix multiplication that we see here. So just reading out what I wrote. The highlighted column of values is the element-wise product of the 0th row of M1, which is our images, and the 0th row of M2, which is our first output, neuron weight. Summing those products would yield negative 10.94. So this object here, this rectangular prism, we're going to call MR. So think of MR as a stack of 784 5x10 matrices. And that's what I've tried to visualize here. Summing those 784 matrices yields the matrix multiplication between M1 and M2. So if we go down to our Einstein summation, which is so beautiful, so eloquent, just one line. Here I've removed the K dimension, and anytime you have a dimension on the left-hand side of this arrow in Einstein summation, and it's missing on the right-hand side, you're telling einsum that you want to sum across that dimension. So again, the shared dimension is 784, so I'm telling it to sum across that 708 dimension. So we run that, we get the same answer, and we are at 80 microseconds, which is comparable to our Numba broadcasting. So that's version 6. Now we're going to go even simpler, even more concise. We have M1 at M2. So the at operator is the matrix multiplication operator in Python, and this is using tensors, so PyTorch. That gives us the correct value. And this is, what is this? 4 times faster than that. So at this point, we're probably like, 30,000 times faster than the nested for loops. So now we only take 20 microseconds to do this. All right, so now the last two, let's introduce the GPU. So from Numba, we imported cuda, and we use this cuda.jit deck. We're going to pass it this cuda.grid is going to be I and j. I haven't gone into detail about what the kind of syntax is for Numba's cuda implementation. So I'm just using the code here and looking at what makes sense. And what makes sense is this item here. This is basically what we had as our final for loop. So we're looking at just one row of A and one column of B, and we are calculating the dot product of that. So what this matmul operation is doing is that we're basically isolating the equal kind of constant dimension element-wise product and summation that takes place. We're isolating that. We have 50 of those because we have a 5x10 output matrix. And so we're going to spread that across the GPU so it does it in parallel. This is again some more kind of boilerplate code. The function that we want to launch is called kernel. We have this grid X and grid Y, which are going to correspond to, let me make sure before I say that. Let's see, launch kernel. Yeah, I think it corresponds to input matrices, but I'm not 100% on that. And then it's going to call the kernel. It's going to pass it the I and j, which I believe is the grid coordinates along with other arguments. So I'm going to create a tensor with zeros that is 5x10, and then I'm going to map all of my tensors, the input and the out, to the GPU. So nothing changes in terms of the shapes. This again is some more kind of CUDA specific boilerplate code that I'm just taking from the lesson. I think this is threads per block. This is how many blocks per grid we have, which is taking the number of rows that we have divided by the number of threads per block and rounding it up, and the number of columns that we have divided by the threads per block and rounding it up. So in this case, we have 1 by 1. And then this matmul function has this like bracket syntax where we pass it these kind of like GPU specific arguments, and then we pass it the actual arguments that we want to perform the operations on. So going back up here, I would assume that this is grid X and grid Y, but I'm not 100% sure on how this translates. Okay, so let's run that. It passes our tests. And if we run this here, surprisingly, this is not as fast as some of our CPU operations. So for example, the matmul operation in PyTorch was 20 microseconds. This is 230 microseconds. So that was interesting to note. We're going to do the same concept with PyTorch, where we're going to transfer our tensors to the GPU. And then we're going to perform matrix multiplication with the operator and bring it back to the CPU. And this is about 2 times faster than the Numba cuda, at least for this small subset. So those are our 10 implementations, and we've done that on our small subset. Now what I'm going to do is I'm going to take the 7 fastest ones, and I did that just for time's sake. I'm going to take the 7 fastest ones, and now I'm going to implement them for our full data set of 50,000 images. So we're going to have a 50,000 by 784 matrix and a 784 by 10 matrix, and we're going to do the matrix multiplication between those two. And here are the results, and we'll look at code next. PyTorch cuda, so this version here where we just transfer over the tensors to the GPU and perform matrix multiplication. That was the fastest at 541 microseconds. And again, this is for 50,000 images. Then there was a significant jump in time to Numba cuda, which was the next fastest at 4 milliseconds. Then the PyTorch operator on the CPU, Einstein summation, similar. And then another big jump was Numba broadcasting, another jump to PyTorch broadcasting, and then another jump to Numba dot product. So taking a look at each of these. So Numba dot product, we are keeping our 2 outer for loops, but our inner for loop is going to use the Numba compiled dot function. And this was 3.71 seconds, so this will probably take a minute to run. I didn't do it for 10 times, but I think this still does it for 7 times. Okay, and here we go, 4.06 seconds. So yeah, a little slower than what I had before. For PyTorch broadcasting, so again, we only have 1 Python loop, and then we broadcast our single image row across our 10 columns, and then we take the sum down the columns, so across the row dimension. I'm not going to run it here, but I moved the tensors over to the GPU, and I ran this, and it actually took more time, so I hesitate to make any conclusions about that, but at least in this case, for whatever reason, how maybe I ran it a wrong way, but it actually took more time to use broadcasting, so maybe broadcasting doesn't work on the GPU like it does on the CPU. I don't know, but that was interesting to note. Okay, now let's get into some of our faster ones. So we have Numba cuda, and let's run it again. So again, we're about 4 milliseconds. PyTorch cuda, which is and just to go back to Numba cuda, we have all these intermediate steps that are the same as before, except now our M1G and M2G is our full X train, which is 50,000 by 784, and the same weights as before, 784 by 10. PyTorch cuda, about 600 microseconds using the operator. Einstein summation, I'm going to remove this for time's sake. So again, the k dimension is shared and it's missing in the output, so it's going to sum across that. It's about 6 milliseconds. Numba broadcasting, same as what we had before, except now we have ngit, so it's compiling it, 662 milliseconds. And then the PyTorch operator just on the CPU is 6 milliseconds. So as a final comparison, I'm going to look at my full data times with the fastest time ranked higher, and then I'm going to compare that to the 5-digit subset time and rank. So PyTorch CUDA was actually the 4th highest when it came to the 5-digit subset, but it scaled much better than anything else, and it was the fastest full data set time. Numba CUDA was interestingly tied at the 5-digit subset with PyTorch CUDA, but it ended up taking about 8 times longer when we scaled up to 50,000 images. PyTorch add operator was in first place with 18 microseconds, but that did not scale well as we went to 10,000 times larger. Einstein summation was third place. Numba broadcasting was second place. PyTorch broadcasting and Numba dot product, those actually maintained their second to last and last place order. So that is my exercise here on reviewing the material in lesson 11 and lesson 12 of the fastai course part 2. So my takeaway from this is, PyTorch CUDA seems to be the easiest, kind of, if nothing else, if works, just chuck that at the GPU and that should do a good enough job. My second takeaway was that something that will be performant on a small subset may not scale well on a large subset. So just because it's fast on a small subset doesn't mean it's going to be fast on a large subset. So that was my second takeaway. Just more generally speaking, when when I'm benchmarking things or comparing performance, just to keep in mind that not everything scales the same way. So that's it for this video. I hope you enjoyed it. Please like, subscribe, comment, etc. And I will see you next time.